Good evening, everybody. I think there are 72 people now, so we'll get started. Others might join perhaps a little bit late. So today is actually the first, technical lecture of Equinox. So let's get started. Today's talk is titled "Understanding Stars Part One." Am I audible?
Yes, ma'am.
Yes,
Yeah,
yes.
yes,
Okay,
yes.
yeah. So today's talk is called Understanding Stars Part 1 because there is going to be a Part 2 sometime later this week. So the goal here is to really make sure that all of you get familiar with the basic, vocabulary of astrophysics and certain physical phenomena and processes that are fundamental in nature, so that all of you have a great foundation going forward into the more complicated, concepts that will be taught in the course. So today we have with us Aman Agarwal. First of all, I want to thank him for being here, being a part of this, and he's probably really busy right now, and he's put aside time to share his knowledge with all of us. So thank you so much, Aman. Um, Aman graduated from BITS Goa, and he has a master's in physics and is right now starting his PhD in Perimeter Institute. So it's wonderful having you here, Aman.
Thank
Once
you.
again, thank you. And I wanted to make a few quick points about how the format of today's talk is going to be. So he's going to be talking for maybe 20 to 30 minutes, and then there will be a short break where you can maybe ask one or two questions. But other than that, we request all of you to post all your questions on the chat box, so that the last 15 to 20 minutes we can have a very productive Q&A session. So even if you happen to leave in the last 15 minutes, it's okay. If, as long as your question is recorded on the chat box, we will address it, so that at least you can go through the recordings again and you will be able to get access to it. So we know that, if you have a question right now, you will probably forget it. So just put it on the chat box and we'll address it later. Point number two, we will have a small quiz for all of you today as part of this talk. Aman has put in the effort and prepared a really, really nice quiz with just around 15 questions. So, what I'm going to do is I'm going to share a link on the chat box so all of you can see it. This will be somewhere around midway through the talk. And the quiz is designed to, just kind of introduce certain concepts to you guys. So that's all it is. And you can just click on the link. You'll have to, I think, write in your, a small name, a nickname or something like that, and it will allow you in. There is nothing too complicated about it. Then there will be a multiple choice, so you can select accordingly. So the minute I change the question, your question will change as well. So it will basically be instructor paced. It's pretty easy to use, so don't worry about it. Aman, you don't have to stop sharing your screen at any point. They will all have a link to their respective quizzes. So yeah, let's get started, and welcome to Equinox, Aman Agarwal.
Okay, thank you, Siddharth, for that kind introduction and that those points about those quizzes and the general rules. I guess one more general rule is I think everyone's muted, so that's great. We can start our talk now. Okay, I hope everyone can see my screen.
Yeah, we can see your screen.
Okay, that's great. Okay, so welcome everyone. My name is Aman Agarwal and welcome to the first talk of this Equinox program. Let's kickstart this program with a talk on understanding stars. So I'll want to give a few disclaimers before starting my talk. First one is I have tried to credit all the information source in the slides, and whenever the slides are shared with you, you'll get to know from where the information has been taken and the relevant source you can consider for further information. Wherever not mentioned, the most of the slides have been taken from the Ignore self-learned material. I'll also provide a link to that later. Uh, this talk would be more information packed rather than theory and derivations here and there. So it would be more of an information filled talk, and that is why I think the quiz will also help a lot, because the quiz will be a little trivia quiz where I'll discuss a few concepts. There will be questions. You'll answer those questions, and based on the answers, I'll dole out few tidbits or trivia about the information which I wanted to convey. So rather than conveying it in a simple plain forward slide format. I wanted to convey it in the form of that quiz. Okay, and the disclaimer about the questions, Sitara already said that you can write them in the chat and we can discuss them during the break or after the quiz. Okay,
Just a second, Aman.
yes,
Is your fan on? We're getting a little bit of noise
okay,
disturbance on.
okay, I'll try to, yeah, one second. Is the disturbance less now?
Yes, yes, very much. Yes, thank you.
Okay, that's great. So, okay, I'll continue. So I started my slide with this little girl, and she's filled with wonderment, looking into the sky. With When I was preparing the talk, the first thing that came to my mind was that nursery rhyme which we have already always read, like "Twinkle Twinkle Little Star," and the questions posed in those rhymes were so uh, relevant even to our talk today. So the questions were, "What are you? Where are you twinkling? And why are you twinkling?" All these questions were there, and these are the questions we'll try to address in this uh, lecture as well. So our quest, we have these questions, fundamental questions about the stars, which are like, what are the stars made of, how do we observe them, how are they formed, how do they die, what do they contain, how many types of stars are there. These are the questions which generally plague our mind. We'll try to answer a few of these questions in a little bit of depth in this talk. So let's address our first question. The first question is, how do we observe stars? I've skipped a few questions because this talk I had to follow a certain time limit. So I'll discuss only three of those questions which I showed in our quest. So the first question which we'll address is, how do we observe stars? So by naked eye, we'll see the visible radiation emitted by the stars, but stars do not emit only in the visible range. They emit in all kinds of wavelengths. Even in the visible range, all stars would not look the same. Some stars look reddish, like if you see at Aldebaran or Betelgeuse, they'll look a little reddish, and some will look blue. The best example I can think of right now of a blue star might be, I think, Canopus, or even Sirius is whitish, a little bit whitish blue. So some will look reddish, some will look white, some will look blue. And there's a science of spectroscopy, which refers to the analysis of the light in terms of its wavelength, and it is that spectroscopy which has been extensively used for hundreds of years to obtain information regarding the temperature, the composition, the age, all the various parameters of the star. So if you look at the slide over here, this is what we call a stellar spectra. This is a colorful rainbow background which has certain black bands here and there. And these black bands are what we learn later. They are called absorption spectra. Uh, we don't mind the axis right now. These axes are labeled by some weird notation, A, B, O, everything placed hither, thither. And there's like downwards, we have some compounds coming in, upwards, we have some atoms. So we'll get to know about them as we progress. So let's discuss the first spectra, which is the emission spectra. For that, we'll get delve into a little bit 11, 12 nuclear theory or quantum mechanics, which we not in the name of quantum mechanics, but what we read about electrons and their different energy levels in 11 and 12. So electrons around the atoms revolve in certain energy levels. They generally do not revolve if you go to a quantum mechanical level, but they reside in certain energy levels. Now, when a higher energy level electron transits to a lower energy level, it will release a certain quanta of energy. And that quanta of energy is emitted in the form of a photon, which is a light quantum. So, this photon will have an impact on the spectra of the material which is emitting light. What will that impact will be? That impact will be a bright emission line corresponding to the energy of that quanta released. Now we know from 11 and 12 that the energy released between two levels is unique to the atom, unique to the energy from which the unique to the electrons transit into an N2 and N1, and unique to the atomic number Z. So this emission spectra is also known as a unique fingerprint of different atoms. So this is the emission spectra. Now you'll be wondering, why did we come to atoms when we were discussing stars? So stars are also made up of atoms, and the radiation emitted by stars will also have similar features. It will have a emission spectra, and later when we discuss absorption spectra, it will also have an absorption spectra. The difference will be, over here I'm discussing about an isolated atom, a single atom. A star is a collection of atoms. And how does that affect the spectra? We'll read later. Basically, it causes a broadening of the spectral lines. But the emission spectra and absorption spectra of a single atom and star are not so different. Okay, let's move on to the absorption spectra. Like in the emission spectra, we had electrons transiting from a higher energy level to a lower energy level. Similarly, if the opposite transition happens from a lower energy level to a higher energy level, we'll have a dark absorption line in the spectra. Now, how would that transition even happen? That would happen if we or somebody else from the outside supplies energy to the spectrum. So that energy can be supplied by the background light, a background incoming light consisting of photon quanta. When it passes through that medium or the star or the atom in question, the isolated atom in question, it will provide photons to the atom, and it will cause the transition from a lower energy level to the higher energy level. So, what will happen to the light which passed through the medium? That light will have photons missing at certain wavelengths, and those wavelengths will have a dark patch, which is the dark absorption line in the absorption spectra. Okay. Uh, in the astrophysical source, we have a background light somewhere from where the radiation is coming, and a star comes in the way, or star or some portion of the star comes in cool portion of the star comes in the way of that radiation, and that cool portion will have then absorption happening of light quanta, and we'll get this absorption line. And generally when we study solar spectra, we study the absorption spectra of the sun, which gives us dark lines, which are also called Fraunhofer lines. If somebody has read about solar spectra, they know that Fraunhofer lines give us a lot of information about the composition of the sun and all its various parameters. Okay, let's move ahead. So we answered our first question somewhat in a shallow way, that how do we observe stars? We observe it using the stellar spectra, spectroscopy, and using spectroscope and spectrograph. It's a whole different science. So let's move on to the second question. How many types of stars are there? And this question will lead to a classification of the stars, and that classification is based on the stellar spectra. And the woman on the left over here, Annie J. Cannon, she first classified stars on the basis of their spectra, and she classified some more than 250,000 stars by observing the strength of the absorption lines, particularly the hydrogen Balmer lines. And what are the Balmer lines? Balmer lines are whenever an electron transits from a higher level to n equals to 2 level. So, particularly observing those Balmer lines, she classified more than 250,000 stars into 7 different spectral classes. And the classification was done on the strength of the absorption lines, how deep, how broad, all these different strength parameters she took into account, and that is how she classified. Okay, so the classification were 7: O, B, A, F, G, K, M. There's a very crude mnemonic to learn this. It's O, B, a fine guy slash girl, kiss me. It's like very cheesy, but okay, it does the work. So she classified it into 7 spectral classes. And then later, this Indian scientist, Mr. M. N. Shah, he said that Mrs. Cannon's spectral classification can be understood. I'm sorry, can be understood with respect to the surface temperature of the star. How is that? The intensity of the absorption lines depend on the surface temperature of the stars, and hence a classification done on the basis of the strength of the absorption lines is basically a classification done on the basis of the surface temperature of the star. Now, how do we relate the surface temperature of the star to the radiation emitted thereof, the absorption spectrum? We'll get to know that a few slides later. It's we also relate it using the black body approximation, but he basically related the spectral classes to the surface temperature of the star. And later, astronomers they divided each spectral class into 10 subclasses and assigned each spectral subclass a temperature to the 5% accuracy. When you change from, let's say, O has 10 subspectral classes, O1, O2, O0, O1, O2, all the way to ON. So O1 to ON will have a 5% accuracy in pinning down the temperature of the surface temperature of the star. So our sun is a G2 star. It lies in the spectral class G and the subspectral class G2 with an effective surface temperature of 5800 Kelvin. Spectral types also give us a lot of information about different stellar parameters. These are the spectral classes have their assigned approximate surface temperature. That is, we also get to know the intensity of the hydrogen Balmer lines, and other spectral features are also known, like O type stars will contain ionized helium, B types will contain ionized and neutral helium, G type or sun type stars will have ionized Ca medium, so calcium medium. Uh, we can also have some naked eye examples of these spectral classes and their visible color. Like a sun type star will always will be seen as yellow, and a O spectral star will be seen as blue. Okay, so these are various informations assigned to different spectral classes. We can also approximate our star with a black body. It has been observed that the outer envelope of a star spectrum is quite similar to the black body spectrum at a certain temperature. So, black body spectrum, if you have studied I think statistical physics, or even yeah, I'm in quantum mechanics, sometimes we study that the black body spectrum, it has a very continuous spectrum across various wavelengths, and it will peak at a certain wavelength. So if we calculate such a spectrum for our star, and if we know the lambda max or the lambda peak, we can know the surface temperature of the star with this very beautiful relation, very beautiful, very compact and easy relation. So the surface temperature is known from this relation. However, the absorptions the spectra of the star, the stellar spectra, is not exactly equal to the black body spectra, because we have dips in the intensity wherein we have the absorption lines. Okay, one parameter we want to know before we progress to a very important topic in astrophysics, the HR diagram, is the luminosity of the star. The luminosity of a star is defined as the total energy radiated by it in 1 second. Now, this energy is in all wavelengths. It's not just the visible wavelength; it is in all wavelengths. But what we observe is the visible magnitude, and we have a scale on on earth. Whatever magnitude of the star we observe, the its brightness, we compare it to the brightness of let's say sun or moon, and we have an apparent magnitude scale. Now from this apparent magnitude, for of all the astrophysical objects, we calculate the absolute magnitude of this that astrophysical object, wherein we calculate what would its brightness be, its relative brightness be, if all the objects were on a 10 parsec sphere around the Earth. We place all the astrophysical objects on the 10 parsec sphere, and we calculate their absolute magnitude. Now, this absolute magnitude, all these apparent magnitude, absolute magnitude are all in the visible range. We want them to be in all the wavelengths, covering all UV, gamma, IR, everything. for the luminosity, and for that a certain correction is done, which is called the bolometric correction. Now, doing the bolometric correction, there are a lot of assumptions taken into place, and using sun solar spectra, we do the bolometric correction, and to each spectral subclass we assign a particular bolometric correction. So do after doing that, we get the absolute magnitude of the star bolometrically corrected, which is this M bolometrically corrected star. And we obviously know the M bolometric corrected magnitude of the sun. Now, we also know the luminosity of the sun. So this beautiful relation gives us the luminosity of the star from these observed values. The luminosity of the star can also be calculated if we know its radius and its surface temperature. And this one comes again from the black body approximation and Stefan's law. We know from Stefan's law that any black body will radiate energy proportional to the fourth power of its Kelvin temperature. So that is sigma T, for this is Stefan's constant, which is multiplied with the surface area of the star. So we get the estimate of the luminosity of the star. Okay. So this formula can be used to derive this relationship, wherein we get rid of all the constants, and we have luminosity of the star by the luminosity of the sun proportional to the radius square of the star, the radius ratio squares, into the temperature ratio to the power 4. So these are just some formulas we use to calculate luminosity, or if we know the luminosity, to calculate radius and different stuff. Okay, now let's come to the HR diagram. HR diagram is a very important, Hertzsprung-Russell diagram is a very important diagram in astronomy and astrophysics, and it classifies stars based on their luminosity and effective temperature. Okay. So if you observe this diagram, there are four axes. Where the left is luminosity, which is directly corresponding to the absolute magnitude. We know from this relationship how luminosity corresponds to the absolute magnitude. Again, we on the top we have the spectral classes, which directly correspond to the temperature of the star, which was deduced by Mr. Emin Shah. And if you see the trends in this diagram, we see most of the stars will lie on this diagonal, which is called the main sequence. We'll discuss some characteristics about the main sequence later, but 90% of all the observed stars lie on, almost 90% lie on this main sequence. The other types of stars which we can see in this diagram are the giants, the supergiants, and the white dwarfs. The giant stars are named so because they are huge in size, and we also see a direct manifestation of this Stefan's law, where the size of the star, if the size increases, the luminosity will increase, and hence the supergiant are at the top of the HR diagram with highest luminosity. Again, if we see white dwarfs are at the bottom left, which means their luminosity is less. Also, one very peculiar thing about the HR diagram is that its temperature decreases as it moves left to right, and luminosity increases as we move from bottom to top. So over here, the white dwarfs are placed. It means that their temperature is really high and their luminosity is very low. Luminosity low being means that the white dwarfs are really small in size. Okay, sorry. Okay, so the diameters of giants are roughly 100 to 1000 times the diameter of the sun, and white dwarfs, as I said, are very hot stars because the temperature, they lie in this range, higher temperature range, but their luminosity is very low because their size is comparatively small. Okay, we were discussing how does the spectrum of an atom corresponds to the spectrum of a star, and that will help us in classifying stars even more. The spectrum of an isolated atom differs from the spectrum of a gas of such atoms by the broadening. If we have a gas of the atoms, those atoms due to collision will lead to the broadening of the spectral line. And this broadening of the spectral line, if the gas is denser, the broadening will be more. So we know from the measure of the broadening how dense is the gas. So the spectral uh, the different stars are even divided based on this broadening into different luminosity classes 1 to 5. And the main sequence is the fifth luminosity class. So our sun is a G25 star, which this total classification is called the spectroluminosity classification. Okay. And if we go to a bright supergiant, its luminosity class will be 1A, supergiants 1B, and so on and so forth. We can see in the diagram. Okay. Have I missed some information? No. Okay. So yeah, I think that is a good point to take a break. I know this load of information escalated quickly from a nursery rhyme to the HR diagram. So we'll take our scheduled break over here for, I guess, 2 minutes, and I can take questions which were there in the chat, and after 2 minutes we can resume the rest of the talk.
All right, so let me quickly ask some of the questions that were addressed in the chat. Um, what is a redshift effect in astronomy? This is by Arti.
Okay, so a redshift effect is basically when the light emitted from the star, the light is emitted at certain peak wavelength, right? I showed in the black body spectrum, the light is emitted at a certain peak wavelength. And if that star is moving towards us, like the
Aman, I think it got muted suddenly. Can you unmute?
Oh,
Yeah.
sorry. So I'll start again. So the stars, they emit radiation at a certain peak wavelength, and that peak wavelength will get shortened if the star is moving towards us. So the wavelength will be shifted towards the bluer regime of the spectrum. And if the star is moving away from us, it's similar to the Doppler effect in sound. The wavelengths are stretched, so it will shift towards the redder extreme. So that is the red shift. I guess you're talking about a red shift or blue shift. You're talking about.
Yeah. Um, how can the spectral information be continuous since the absorption lines are unique and shouldn't they be discrete? This is by Dwidge.
Okay, so continuous, what we say is continuous is the background spectrum. We have a background spectrum, the Vibgyor and other spectrum, and on that background spectrum, we'll have black patches, which will relate to uh, the different absorptions which have taken place. And by discrete, I I think you mean shouldn't they be sharper? So they'll be sharper if it is an isolated gas, but if it is a sorry, isolated atom, but if it is a gas of atoms, those black patches will get broader. So we'll have discontinuity in the spectrum. That is true, but by continuous, I mean the background spectrum is continuous, and on that we'll have some black patches.
Yeah, and as a continuation, he asked if they are discrete, there would be a lot of gaps. So, how would you find the absorption lines?
Um,
I think, yeah, I
I
just think. Uh-huh.
Yeah, go on.
No, I think he means if there are absorption lines are very discrete, then you would find, I guess, broader in width. The absorption lines itself might be wider. So, how
Yeah,
would you more precisely point out exactly what the absorption line is?
yes. So we have like very well defined spectral templates. The spectra you observe, you run it through the templates and you match to the template. So let's say TiO2 will have a template, hydrogen will have a template, and a star doesn't contain one element. It will contain many different elements. So the spectra which we'll get will match in parts to many templates, and then you'll take a combination of those templates and you'll infer, okay, we have a calcium because I have a dip in the spectra in the calcium regime. We have some carbon because I have a dip in the carbon regime. So the spectra over different wavelengths will have different characteristic dips, and using these dips you will understand, okay, which element it is.
Okay. Next question. This is from Chakradar. Do you correct luminosity for the interference from other luminous sources?
Okay, that's really good question. So, interference, now you need to understand that all this information is being collected with good precision, and it is being collected by localizing the space of observation. So you have different telescopes or other medium from which you localize the observation space to that particular star or minimum interference region, and so we can have good confidence in the data we have collected.
Great. Um, okay, I think which stars? Okay, I think that comes in the quiz, so I'm just going to keep that question
Okay.
for later. Okay. Um, yeah, I think we can move on. There is a question about, I think, cosmic background radiation
Okay.
and the detection of it. What instruments are used to detect? Maybe you can quickly address it, even though it's not directly related.
Okay, so CMBR, as far as I know, it's in the radio wavelength. Correct me if I'm wrong, if anybody else knows better, but as far as I know, it's in the CMBR is in the,
Microwave, yeah.
sorry, yeah, microwave, I'm so sorry, microwave ranging, and so cosmic microwave background radiation. And I, I, I don't think I have a good answer on what is used to detect CMBR.
Yeah, I think the instruments are very similar to radio telescopes, but
Okay.
they obviously have to be much more precise. So you can look up some of the different. Currently, Planck is the satellite that is most well known for detection
Nice.
of CMB. So I think you
Okay.
can look that up. I think with that, we will stop and continue Q&A at the end of the session.
Cool. Okay, so let me continue with the talk. And I hope till the quiz we'll have more information in our in base so that we can get most of the answers correct. Okay, so let's proceed to the information that can be extracted from this HR diagram. I said that the HR diagram is a so sorry, yeah, HR diagram is a highly useful diagram. Why is it so useful? By the position of the star in an HR diagram, I can know its age, I can know its size, I can know its luminosity, I can know its mass, spectral type, absolute magnitude, surface temperature. All this information can be extracted by its position in the HR diagram. And also remember that the position of a star doesn't remain constant in the HR diagram. The star moves, it traces a path in the HR diagram as it progresses. Uh, so let's go to different information bits one by one. So the first is age. Uh, Most of the stars are in the main sequence. So what does that give? What information does that give to us? Uh, 90% of the stars are in main sequence, and main sequence is called as the zero type sequence. I'm so sorry, I leaked a quiz question now. Yeah, it's called a zero age main sequence because most of the stars start in the main sequence. We say that when a star enters the main sequence, it is quote unquote born. So if a star is in the main sequence and that too on the upper left part of the main sequence, then we know that it's a relatively younger star. On the lower right part, I know that it is older. It may be older than the upper left one. I know if it is a giant, it is definitely older than the main sequence star. And why do I know that? I'll discuss that when we go to the stellar evolution. So the age is known depending on the cluster it is present in, the star is present in. Size I discussed. As the luminosity increases, the we know that the size of the star is more because L is directly proportional to the radius square. uh, Luminosity, spectral type, absolute magnitude, and surface temperature are just the axis of the HR diagram. So they that information is very readily available. And mass, again, mass I'll get to later, but most of the stars have a luminosity mass relation. And if I know the luminosity of a star, I can uh, at least in the main sequence predict its mass to very good accuracy. So that gives us the luminosity from the HR diagram will give us the information about the mass of the star. Okay. So now I wanted to show a stellar evolution video developed by Ohio State University. So let me just stop sharing this screen and start that video screen. Okay, I hope the video is visible. Please let me know if it is not. Let me start the video. So this is the star cluster evolution in the HR diagram. They have, once again, they have simulated the evolution of a star cluster from the age of 100K years to 19G years, plotted on the HR diagram. And what's a star cluster? Star cluster is basically stars of different size and luminosity taken as an initial configuration. And that initial configuration is dumped on the HR diagram. I'll show you. So this is the initial configuration. They have just randomly generated this initial configuration of stars. So this cluster contains about, I think, 30,000 stars with different metallicity, different luminosity, different surface temperature in the initial state. And then we'll see how this cluster will evolve, how it leads to different main sequence star, white dwarfs, and different giants. Okay, so the cluster has 30,000 solar metallicity stars. These are just the initial values given to the evolution model which they have followed. The stellar evolution models which they have taken are from the MIST database. You all can like Google more about it. There are different evolution models which take into account uh, the different metallicity, the initial mass configuration, the initial abundance ratio, everything, and they give us the different stellar evolution pathways in the HR diagram. Okay, so this is the initial configuration which has been dumped on the HR diagram. And as you see, as the time progresses, the stars, they come around the main sequence line. But some stars run off to the giant phase. Okay. And from this giant phase, we have white dwarfs coming in over here. And at the end, all of the stars which were over here, I'm sorry, which started over here, all of the stars which started over here confined themselves to this part of the main sequence. There are some red giants and some white dwarfs. Where are the giants? If you observe the giant, the number of the giants is decreasing, fluctuating, it's not remaining constant. Same is of the white dwarfs. Where are they going? There are different processes happening in stellar evolution after the giant and white dwarf formation. There is supernovae and mass accretion binary system. All these different things come into play. So the number over here and the number over here fluctuates as the cluster evolves. And this simulation only takes into account the main sequence, the giants and the white dwarfs. The compact stars are not taken into account. Okay, so this is the end of the simulation. Let me stop this share and come back to my slide. I'm sorry, it just keeps going back to that. I don't know why. Okay, let me try this.
You can also share your whole screen in case it's a problem.
No,
Yeah, it's going back to that. Maybe
it
you can.
just keeps going back to that for some reason. Just close that window.
Yeah.
Okay, so I guess now I'm back to my slides.
Yeah, we can see it.
Okay. So now we are answering the question that how are stars formed and how do they die? And that was precisely what I wanted to show in that stellar evolution on the HR diagram. That if I take an initial mass configuration, what path will they trace on the HR diagram? Okay. When we discuss stellar evolution, once, yeah, when we discuss stellar evolution, a natural question to ask is how did the chemical elements which we see, which are the building blocks of all the living and non-living matter, how do they come into existence? So now right now it looks like apples and oranges. Like we are discussing stellar evolution, and I went into chemistry. But the thing is that most of the elements, apart from hydrogen and helium, are synthesized in stars or objects in stars, clusters, and galaxies. So how are these elements synthesized? That is the question precisely answered in stellar evolution. So that is why when we discuss stellar evolution, nucleosynthesis and the element production and element abundance is a very natural question, or a byproduct, I should say, which comes to us. There's one very interesting fact that the abundance of different naturally occurring elements on in the solar spectrum or in the solar system or in the universe, it is relatively same, and it's called the cosmic abundance. So this relative proportion of elements, cosmic abundance, which is similar in different size scales, how is that happening? And that also comes from it does comes from particle physics, nuclear physics, and it also comes from the source of these materials, that is the stars. And there's a famous I don't know who said that, but there's a famous line like we all are made of star dust. So that is precisely what is uh, this chemical production or nuclear production in the stars, which is called nucleosynthesis. uh, the abundances, the trend followed by the cosmic abundance is such that up to the mass number of iron, that is 60, the abundance generally increases, and after that it decreases. So that is there because the iron nuclei has the highest binding energy per nucleon, which makes it the most stable nuclei. So that is why the abundance of the iron nuclei is the peak abundance in the relative abundance graph. So if we start from the very beginning of stellar evolution, we see that a collapsing cloud of gas will collapse into a protostar, which is a baby star, and that collapse has a whole lot of dynamics into it. There's a very vibrant field of research, star formation. There is genes criteria and different criteria that gas has to follow for it to collapse into a spherical protostar, excuse me, almost spherical protostar. And that protostar is still collapsing. A protostar is not stable, it still collapses. Okay. And it collapses till it reaches the main sequence line, till its luminosity and surface temperature reaches the main sequence line. And that is where the temperature of the core is high enough to start nuclear fusion process. So the hydrogen burning to produce helium starts. Okay. So let's discuss about main sequence star. I said that on the main sequence line, the hydrogen fusion will start. The hydrogen fusion occurs by these two processes, the proton-proton chain or the CN cycle. I have never memorized these cycles. And I do not suggest anyone to memorize these cycles because I have seen CNO cycles having a lot of complexity, like a huge CNO cycle with a lot of catalysts and lot of protons, neutrons, positrons, neutrinos flying here and there. So this is, I think, a very bare minimum form which I've chosen. But the basic thing over here is the four protons are being fused to form a helium, and over here the similar reaction is happening. The carbon and nitrogen act as a catalyst. The stars which only drive through pp fusion, proton-proton fusion, are are called the first generation stars, and they cannot have the CNO cycle because they don't have carbon and nitrogen in the core. And why don't they have it? Because they are relatively older stars, which were formed, like the first stars which were formed in a galaxy or in a medium. And these stars do not have the heavier elements provided from the medium. These stars fuse these heavier elements in the core as they evolve, and when they go supernovae or when they release flashes, these heavier elements are kicked out into the interstellar medium. And from that interstellar medium, when second generation of stars form, they already have carbon and nitrogen in their core, so they can start the CNO cycle, and they are called the second generation stars. Okay. Another thing about main sequence stars is stars on the main sequence have a very well defined luminosity mass relation, which I had alluded to earlier when we were discussing about the benefits of the HR diagram. So the luminosity of a main sequence star is proportional to its mass to the power of 3.5. So if I know the luminosity of a main sequence star, I can very well find out its mass. And also, if you remember I'm sorry if I don't remember if I have placed that equation in the slides, but there is a equation connecting luminosity to the time spent in the uh, main sequence. And that is because luminosity is a measure of how much radiation is going out. So that will give us in term a measure of how much drying up of the core is happening, how much fusion is getting depleted. And that fusion depletion will give us a time estimate of how much time will that star spend in the main sequence. So the time spent in the main sequence is directly proportional to the sorry inversely proportional to the mass square 2.5. So the more massive a star, the less time it will spend in the main sequence. Okay. So we discussed about main sequence stars. What happens after the main sequence star? We know in the main sequence star, hydrogen fusion is happening. But when all the hydrogen is burnt up, the radiation pressure. This is one thing which I missed in my previous section is the protostar is contracting, and it will contract to a point when the hydrogen fusion starts. But what prevents further contraction? It is the radiation released from the hydrogen fusion. That going out radiation will have a pressure, and that pressure, radiation pressure, balances out the gravitational tendency or the force to contract. Now when this fusion reaction will stop, this radiation process will pressure will also decrease, and the core will again start to contract. Now this, from here on, different pathways are followed by the star depending on its mass. For lower mass stars, what will happen is a shell around the core, that shell will start fusing hydrogen, because when the core is contracting, its temperature is increasing and the surrounding temperature is increasing. So that thin shell will start fusing the hydrogen, and it will start forming helium. Now since that thin shell started forming helium, its mass increased, and it will again fall upon the core. The core's mass increases, so the core will again contract quickly, and that will again reach to a greater increase in the temperature. A greater shell will again fuse helium, and so on and so forth. A sort of a runoff process will go on. And this core contraction, it releases a lot of energy into the envelope, into the outer envelope, which is not in that thin shell which is fusing the hydrogen. So that outer envelope uh, gets an accelerated shock of energy, and so it expands, and that expansion leads to the increase in the size of the star, and we have something called a giant star which is formed. Now that giant star, since its radius is so huge, its area is so huge, its luminosity is really high, but its surface temperature is very low, because in the expansion it has radiated a lot of energy, and it has cooled down, the surface has cooled down. For more massive stars, what will happen, this cycle of contraction, okay, yeah, the when the core is again contracting, in the inner part of the core, more heavier elements are being formed. The shell is forming the is fusing the hydrogen, but the core, which is contracting and its temperature is increasing more than the shell, that will start forming the heavier elements. And this heavier element synthesis, and as I said, the contraction is a little accelerated, so the heavier element synthesis also gets accelerated till all the nuclei become a iron nuclei, because after iron nuclei the binding energy per nucleon decreases. So the most stable is the iron nuclei, and it will stop at the iron nuclei. It won't stop forever, but it will stop for a certain time. And elements heavier than iron require different, more extreme conditions to be synthesized. Okay, so so I discussed two different types of stellar evolution over here, the low mass and the heavier mass stars. Let's first focus on the low mass, that is solar mass stars. And solar mass stars, a star of a mass approximate to that of sun, when its hydrogen fusion will stop, it will abruptly start burning helium, and a large amount of energy is suddenly released. This abrupt helium burning, due to some processes, the helium burning is really abrupt, and it will it's an exothermic process, so it will release a whole amount of energy. And that amount, that sort of explosion, sort of flash, is called helium flash. This helium flash is not completely understood. So if there are questions specific to the helium clash, I'll defer them to later, and I'll also ask somebody or senior who are researching in this to get to the particular answer, because this is not a very well understood phenomena. But we know that this helium flash, when it occurs, it releases the inner part of the star, and there's a whole lot of diffuse material around the star. And when we observe it through a telescope, it it looks like a planet surrounded by dust. And like, I observed one planetary nebula, and it really looks like a spherical ball which has a lot of dust particles around it. So that is why this thing, which this outer envelope and this small mass star, is called a planetary nebula. And the gas surrounding the main part of the star, that gas is diffused quickly due to the interaction with the interstellar medium, but core contraction is not stopped due to this helium flash. The core is still contracting, and the core contracts till it breaks down its constituent elements. The elements inside the core are broken down into electrons and nuclei. Now this electron, it forms a degenerate gas. What is the degenerate gas? We know from quantum mechanics that the electrons occupy certain energy levels, and from Pauli's exclusion principle, two electrons cannot occupy the same quantum energy state. So what will happen, these electrons, it will be like a giant nucleus surrounded by electrons, and these electrons will start occupying the lower level first, and then the electrons will start filling up the higher levels. But the electrons which have not yet filled a level, they won't be allowed to fill the lower level, and they'll face a certain pressure from these low filled electrons, and that pressure is called the electron degeneracy pressure. That arises solely due to the Pauli's exclusion principle, and that pressure is enough to hold the further contraction of the star up to a certain mass limit. Okay, so that mass limit was given by famous Indian astrophysicist Dr. Chandrasekhar, and Dr. Chandrasekhar gave this limit that a mass, a star of mass 1.4 solar mass will be prevented from further contraction by the electron degeneracy pressure, and that degenerate gas is called white dwarf. A white dwarf, as we saw on the bottom left of the HR diagram, they are very hot stars with very low luminosity. Because they were contracting in the first place, their luminosity is less. And again, due to the contraction, their temperature is really high. Excuse me. The limit 1.4 solar mass put by Dr. Chandrasekhar is also called the Chandrasekhar limit, and I got to know that a few people are working on this in their mini project in this program, and that's great. And let's see the derivation. We will see in that project how you derive this Chandrasekhar limit. It's like very beautiful. There's a graphical derivation, as far as I remember, very beautiful derivation. But yeah, we can see different, explore different ways of deriving this. Okay, so let's move on to the more massive stars. So the lower mass stars are now finished. They have this very beautiful way of, first from the main sequence they will go to the giant phase, then form planetary nebula and end up as a white dwarf. Stars of the intermediate range also eventually end up in the white dwarf, like from 1 to 10 solar mass, or sorry, around 5 solar mass also end up in the white dwarf phase. But they have some oscillatory motion and then they end up in the white dwarf phase. More massive stars, 10 solar mass or something like that, the iron nuclei has been formed, and the nuclear reactions that in those iron nuclei after after iron formation halts. But the core contraction has not halted. The core is still contracting under its gravitational energy, and electron degeneracy pressure is not enough to hold this core. So this core contraction will break down the iron and all the other nuclei formed. So all the different nuclear reactions which have happened, all the work that has been done, now it is being taken apart by this core contraction, and this nuclei will be broken down into the nuclei of helium, and it will be broken down till we have protons and neutrons. Now, this is the core. I'll get to the core a little bit later. I'll discuss the envelope now. This core breaking down is an endothermic process. It requires energy, and that energy is given by the gravitational contraction. So, if I start the process, gravitational contract feeds the energy. So the endothermic process accelerates. That in turn accelerates the gravitational contraction, and so on and so forth. So this core collapse is accelerated, and what it does is the gravitational contract, uh, it feeds the endothermic process, as well as it releases a lot of energy in the envelope. It lead it releases explosive amounts of energy in the envelope. Okay, so let's discuss the envelope dynamics. Now the envelope has relatively lower mass elements. The core had synthesized till iron. So when this energy is released, these lower mass elements start going nuclear fusion till iron. And when there's like a runoff, there's a explosive amount of energy released in the envelope. This envelope just goes boom in a supernova, and that supernova releases a huge amount of energy into the interstellar medium. It releases supernova shock. It releases a lot of energy, it releases a lot of heavy elements which were synthesized before the explosion. So it really enriches the interstellar medium to form second generation stars, or heavier element, or different astrophysical objects. Okay. Uh, so the supernova is also classified into different types. It is classified into different types based on its light curve. What is its light curve? We map the brightness of the supernova as time progresses. So if the supernova is really bright near the explosion, but that brightness dims really fast, then it's a type 1 supernova. And if it is relatively lesser bright, but that brightness decreases with a lower slope, then it's a type 2 supernova. Now, even in type 1 supernova, there are two distinctions, type 1a and type 1b supernova. Type 1a supernova is generally credited to white dwarfs. But I had said white dwarfs are supported by electron degeneracy pressure. So how are white dwarfs exploding in supernova? What happens are many stars are in binary systems. So or many stars can accrete mass from the interstellar medium. So when white dwarfs start accreting mass from the interstellar medium or from their binary companion, their mass grows, and as soon as it passes the Chandrasekhar limit, the core contraction starts abruptly, and then there's a supernova. So you can see that all these white dwarfs will abruptly go supernova at 1.4 solar mass. So the characteristics of those supernova will be very similar. And that's why a type 1a supernova curve is very precisely measured. It has a very precise template. And if I have a unknown supernova light curve, I can, if it matches with a 1A type light curve, then I can easily say that it is a white dwarf which has gone supernova. Type 1b supernova are also there are different light curves for type 1b, and they are thought to be due to carbon burning in the degenerate core of different stars. They like, I had the helium flash, there's a carbon flash, and there's a whole lot of processes attributed to that. And let's go to type 2 supernova. Excuse me. Type 2 supernova is not the same for all uh, uh, astrophysical processes. Like type 1A is a characteristic curve, type 2 is not. Type 2 is distinct for different observations. And that is why it gives us the intuition that these might be neutron stars and sorry, not black holes. These might be neutron stars, or the processes leading to black hole going supernovae. That forms a type 2 supernova. So now, what are neutron stars and black holes, which are clubbed together as the compact stars? I had discussed over here. I had taken a detour and started discussing about the envelope. The core is still contracting in a endothermic process, and it's breaking down its nuclei into helium and then protons and neutrons. Now neutrons, like electrons, follow the degeneracy, the Pauli's exclusion principle, and have a neutron degeneracy pressure. So that neutron degeneracy pressure can hold a certain amount of mass, and that mass is about 2 to 3 solar mass. So if the star which has gone supernovae, when the star goes supernovae, it ejects out a lot of material in this interstellar medium. So a 12 mass star will yield about a 2 solar mass to 3 solar mass core, and that core can be supported by neutron degeneracy pressure. But if the core of the core is weighing more than 3 solar mass, then the gravitational contraction cannot be stopped by any further process, and it will form a black hole. Now, black hole is a very interesting topic in astrophysics, astronomy. A lot of research is going on in this topic, and the first gravitational waves which were observed were also from binary black hole mergers. So basically, all we know from we all know from popular science that black hole is such a strong thing, that gravitational field, that even light cannot escape it. This popular line is not so correct when it comes to GR, that the light cannot escape it because of its gravitational field. No, if anything goes inside black hole, the circumstances are such that the the timeline of the object, the time only progresses inside the black hole, it cannot come outside. So there are like very different dynamics in GR when you go to general relativity, and again you have quantum gravity effects and different effects coming into black holes. So it's a very vibrant and vivid field of research. So these are the two compact objects, neutron stars and black holes, which are formed after the supernova. It releases. Okay, it is released after the supernova. So now I guess I'll go to the quiz. So there's a lot of trivia information which I want to also discuss in relation to the talk, but that I'll discuss via the quiz, so that there's an interactive part over here. And Sitara, you can give them the link. They can start, but I would request, like, you go through the first question and then let me explain the first question's answers, and then you proceed to the second question, if
Yeah.
that's okay.
So the way this works is I can control sort of when to go to the next question. So
Okay,
I'll maybe just read the question, you can explain it, and then I'll go to the next.
sure. Okay, we can start the quiz now.
Okay, so I'm just going to paste the link, everyone. I'm putting it on the chat box. So you have to go to that link, and I think it asks for a nickname or just make sure you put your first name and you don't make up like some weird name because we want to kind of keep a track.
Yeah.
And then I think you can, I'll give you guys 30, 40 seconds, and then I'm going to say start. So it will start for everyone at the same time. Okay, I see 13 participants now. I'm just going to wait for you guys.
Okay. Let me mute myself, and Sitara will tell the questions, and then after each question, if I have to add something, I'll just unmute myself.
Okay, 40 participants. Okay. By the way, guys, this works for your phone also. So even if you're on your phone, it's okay. You can just type your name and wait for the quiz to start. Okay. If anyone's having an issue, you can probably put it on the chat box, and Jivan can kind of address it.
Sure.
Okay. Should I start? Uh,
54 people have joined.
55. Yes. Okay, I think I can. I'm going to go ahead and start. There seem to be how many people on the call? 66. So I think around, I guess, excluding the three of us, there are probably seven, eight of you who have not joined the quiz. So I'm just going to get started anyway. 61, 62.
Maybe we should
Okay.
wait. They're all joining.
All right.
One more, one person. Yeah, start.
All right, everybody. I'm starting the quiz now. Okay. Doppler effect shifts the wavelength of the stars moving away from us. So, okay, I see a lot of you answering it. Okay, I think most people have answered it. So,
So I had kept this question to discuss Doppler effect later, but I guess in the break we discussed Doppler effect. So I hope most of you have answered it correctly.
yeah, so the way it works is there are 30 seconds to each question. So I'm going into this question number 2 now. So after 30 seconds, Aman, you can maybe comment about it, but let's give them the first 30 to kind of just answer.
Sure.
Extremely hot stars do not produce absorption spectra. I think there's a true or false question. So. Okay, some of them are thinking and answering. All right. Three of them are yet to. Okay, time is up. Aman, any comments about
Yeah.
this?
So if you would know the answer, it's true because extremely hot stars have ions instead of atoms. So the electrons do not have any level they can transit. So extremely hot stars do not produce any absorption spectra, and extremely low temperature stars also won't. Not even extremely low temperature stars won't produce an absorption spectra too, because the temperature wouldn't be enough to cause the Fraunhofer transition or the Fraunhofer lines to appear. So the low temperature stars or extremely high temperature stars do not produce an absorption spectra.
Okay, I'm going into the next question. I hope everyone got that cleared. You can always come back and kind of ask about it. Stars with low luminosity generally have a lower effective temperature. Uh, Aman, just personally, is this referring to apparent luminosity or kind of like absolute, just the luminosity, right?
Yeah, so luminosity, I am not referring to the observed magnitude, it's the luminosity, the L, which is derived
Intrinsic.
from the intrinsic from the absolute magnitude of the brightness.
Okay, I see that three people did not answer that question. So, guys, even if you're not too sure about it, just give it a shot.
Yeah,
You can always
there's no
learn.
negative marking.
Yeah, there's no negative marking here.
Yeah. So
Uh,
if you would know the answer to that question, that answer is false because one second. have to read that question. Uh,
Yeah, stars with low luminosity generally have a lower effective temperature.
Yes, so that's stars because for us, because we know about white dwarfs which have very low luminosity but very high temperature. In the HR diagram, we have that. So the temperature is not generally different, dependent on the luminosity. The temperature is dependent upon different factors like how is it forming, what is the process that is driving to the increase in the vibration or the increase in the internal energy of the core. So yeah, that's a false statement.
Okay, going into the next one. Um, which stars are called zero age stars? So I think he kind of mentioned this already in the talk. So we'll know how many people were not paying attention.
Yeah, that's a good check
Yeah.
whether people were asleep or not, or just we.
Come on, guys. 2 seconds left. 2 seconds. All right. Okay. The leaderboard for this is okay. All right. 43 got it right, but there were a few people who got it wrong. So, yes, I
Okay,
think I think 19 people really have to stay awake for the rest of the talk at least.
okay. So yeah, I'll just repeat. 0 8 stars are the main sequence stars. When a star enters the main sequence, it is quote unquote born. So that is why it's called a zero age main sequence star.
The brightness of two stars at the same temperature is proportional to, and yeah, like I've mentioned there, you can select all that app apply. So again, I think the trick here is to really understand what brightness is referring to, and the point that it is not just related to temperature, right?
Yeah, so you can consider brightness over here luminosity or the amperant magnitude. If you consider luminosity, you'll get the second answer, which I put. But yeah, consider it luminosity.
Yeah, I mean, I think a lot of people didn't even attempt this one because I think they were like looking at the question.
Okay,
But they did get it right. A lot of them got it right.
nice.
But I
So
think, yeah.
okay, so sorry for framing this a little vague, but by brightness I meant the luminosity, and I gave you that formula. L is 4 pi r square sigma t power 4. So at the same temperature, T is constant, all the other factors are constant, so it's just L proportional to r square. So I kept two answers for this, radius and radius square, because I hope that if anybody just clicks radius in a hurry, they would also be correct. But yeah, L is proportional to r square. That's the formula.
I have a question. I answered radius squared and distance of the star, but it says I'm incorrect because radius is also an answer.
I guess you
It should
would
be
have to
correct,
give.
right?
Yeah, it should be correct, but not the distance. L is not dependent on the distance. Luminosity is not dependent on
Mm.
the
But
distance.
it says brightness. Brightness
Brightness.
of the star is
Okay, yeah. So yeah, that is my fault. Okay. So
Yeah,
yeah, sorry for that
Yeah, the
vague.
same thing happened to me.
yeah.
Okay.
to
It
me
shouldn't
also.
be proportional to the radius.
Yeah.
Same thing happened, but I
Yes.
also chose radius.
Both B, C, and D would be correct.
Ah, okay.
Yeah. So Sitara, if is there a way to disqualify this question, let's disqualify it, or we can just move on.
Okay. As we move left to right along the HR diagram, effective temperature decreases. It's a true or false question. So,
Again, this is a check whether you were paying attention.
yeah.
A very basic question if you paid attention in HR diagrams.
Cool. I think most of them got this one right.
Okay, that's great. You can go on.
Yeah, moving on. So, how many spectral subclasses are there? Just give it a shot, guys. I see a lot of people you've not yet answered. There are 3 seconds left. Two, one. Oh. Aman, would you like to comment a bit about this?
Yeah. So, like I said, there were seven spectral classes. O, B, a, fine, guy, girl, kiss me. So seven, and each spectral class has 10 sorry, differentiation. So 7 into 10, 70 subclasses.
70. 22 people got that right. Okay, moving on to the next question. Subsolar ZAMS stars die younger.
So ZAMS is zero age main sequence.
Aman, when you said younger here, you're talking in reference to the sun itself, right?
Yeah, to the sun or to the heavier stars.
Heavier stars, right?
Yeah.
Okay, yeah, you can explain it a bit.
Okay, so subsolar is basically stars with masses less than Sun, and ZAMS is they lie on the main sequence. So I guess 30 seconds are over, so I'll get to the answer then. The answer is false because I had said mass is directly proportional, so inversely proportional to the time squared 2.5. Time spent in the main sequence is inversely proportional to the mass squared 2.5. So if the mass is less than sun, then it will definitely stay more in the main sequence than sun. And also you can understand it by if the yeah, luminosity depends on radius. So yeah, the mass time relationship is defined is derived from the luminosity, and the less massive the star, it corresponds to lesser size, so lesser luminosity, and lesser luminosity means it will radiate slower. So since it radiates slower, it will stay in the ZAMS line for longer. That's why it's a false statement.
Cool. Okay, so the next question is pick all that apply. Older stars in a galaxy, and the options are called pop 2, pop 1, contain much more heavier elements than younger stars, contain much lesser heavier elements than younger stars. Okay, 25 seconds left.
What is pop?
Pop 2, Pop 1 is a population 2, population 1 star. It's a classification which I have not yet introduced, but I just wanted you all to guess right now.
This is actually slightly tricky, but it's interesting. Um, okay. Yeah, time is up.
Okay, so if you know the answer is they are called the population 2 stars, and they contain much less heavier the elements than younger stars. This I had explained in my talk that the older stars of the galaxy or of a medium are formed with the only the hydrogen and helium, and they do not have the heavier elements in their core. So that is why the D answer is correct, and they are called pop 2 stars because the population classification is based on metallicity. So since they have lower metallicity, lower lesser heavier elements, they are called population 2, and population 1 is the star category which has higher heavier abundance. So there will be carbon, there will be nitrogen, there will be uh, oxygen and iron and all those things. They are called the population two. So I kept this question to also give a contrast to the first generation and second generation stars. The first generation stars will generally be population two stars, and the second generation stars will be generally be population one star. Yeah, you can go on.
Yeah. CN cycle following stars are generally found in the HR diagram. Um, yeah.
What do you mean by CN cycle?
There was the CNO cycle which I showed when we did the nucleosynthesis part. Let me just show you 1 second.
Okay.
Yeah.
Time is up, but yeah, you guys can look at this screen for
Okay.
a sec.
Yeah. So this was the CN cycle. This was, I said this was the proton-proton chain, and this was the CN cycle. So the main thing for this one was the CN cycles. The correct answer is, let me see the options. They are in the upper part of the main sequence. So that generally comes from the upper part is more luminous, and more luminous it means it's more massive, and more massive is indication that the heavier elements are present in the core. That is why the CNO cycle burning stars are generally found in the upper part of the main sequence. We know that the main sequence stars will burn CNO, will have a CNO cycle and PP chain, but the upper part generally has the CNO cycle.
I
I
have a
have a
doubt.
question about the. Okay.
Yeah, go on.
Even giants are at the upper part, right?
So giants are over here. 1 second. Let me get to the HR diagram.
Upper right, right?
Giants are over
Upper right.
here.
Mm.
Uh, I don't know whether I put
This
super
option
giant.
just says upper part of the main sequence, not upper part of the diagram.
Yeah, yeah, that's why I put upper part of the main sequence.
Okay.
Okay. Is there any confusion? Okay, so I think we can go on.
No, can you wait? Like, I have a question about the last question. Like, uh, the older the star is, the more fusion occurs, right? So, more elements should form, and more the elements, the more heavier they get.
Yeah, so the older stars are the first factory of these elements, and they produce this element and throw them off. Okay,
Oh,
so yeah, so that is why their metallicity is generally lower. While the second generation stars, they start from accreting this element and also fuse it. So that's why their metallicity is relatively higher.
heavy. Okay, okay.
Yeah.
Okay, guys, I'm going to the next one. The stars enriched by material released in the ISM by supernova are called.
The
ISM is
ISM is the
interstellar
interstellar,
medium.
yeah,
Yeah.
interstellar medium.
I think this is relevant to the question that I think
Yes,
Vishal just asked.
yes.
Yeah. Okay. 2 seconds left. Yeah. Most of you should have gotten this right. I think this is exactly what Aman said now.
Yes.
So
So
basically, they're
if the
second generation stars, right?
yeah, they are second generation stars because they already have the material accreted from the interstellar medium, and also they are fusing it, so their metallicity is relatively higher. Yeah. So the next question, you have to refer to this diagram which I have shown in the screen.
I'm going to disable timer for this particular question. So you
Sure.
guys can take a look at the Zoom screen. Mm,
So I'll give a hint. This I had shown different types over here, but I missed 2 3 types. And from over here, from the characteristic I told over here, you can gauge over here the curve, but after that there has to be a guess also in this one.
Okay. So I'm going to kind of end the question in maybe another 20 seconds. So please attempt it. Yeah. And maybe, Aman, can you just show the previous slide once more, perhaps,
Yeah,
for others who want to just see it once?
yeah. And also remember, while I was discussing this slide, I was discussing about different curves, what are characteristic curves. That's a hint.
Okay, I'm gonna go ahead and end the question.
Okay, so should I say the answer?
Yeah, one sec. I think there are two more people yet to attempt.
Okay, just
Can
take
you
a
guys
guess at
just,
this
yeah,
point.
take a guess, guys.
Yes.
Don't overthink it. Okay, yeah.
Okay, so the answer is type 1A. See, I don't expect you to have light curve templates. So I'll obviously give a characteristic curve. So from that, you should know that this is a 1A because 1A has a characteristic curve. It does not, it does not differ according to the situation. And this is a type 1 supernova because there's a very rapid decline in the brightness. And if you if you do a crude matching to the to this diagram, you cannot do that because over here the brightness is already dimmed to its previous value. So over here we'll cut off the curve, we won't go much further. So that's why the decline of the majority brightness is very rapid. That's why it's a type 1 curve. Okay, yeah, we can go back, go on.
And type 2 curve, do you have an example for how it would look?
This would be a type 2 curve, which
Okay.
will in the starting it will have a rapid decline, but the majority won't be spent in a rapid decline. It will have a gradual decline in comparison to a type 1. You can see the slope over here is more, it's less than the slope of a type 1 star.
All right, I'm going into the next question. Yeah, we have around two questions left.
Yeah.
So, what is the name of the nebula left behind by a supernova recorded by Chinese astronomers in 1054 AD? This is,
So,
you have 20 seconds left, guys. Yeah.
yeah,
And
so
Ma'am,
the,
options.
there are two crab nebula in here.
Oh, really? Oh,
Yep.
okay. I mean, just pick one.
yeah. So there's some trivia about this. Like this is said to be Chinese astronomers recorded it as a bright flash in the sky, and they said there was light even when the sun set for some 1 or 2 days. It was so bright. The supernova was so bright.
Okay.
Okay, I think it has ended, and we know the answer. It's Crab Nebula, and if you see, it's a very beautiful. The photograph, if you Google nebula, the first photograph I guess comes from a Crab Nebula. So you can see the neutron star left behind also if you observe it through a very advanced telescope. Yeah. So this was the
Neutron, one sec. I think it, okay, I'll disable the timer for this one. Yeah, you can continue.
okay. So what was I saying? This was one of the very first recorded observations of supernova. I guess if there are observations before this, I don't know whether we have classified them as supernova or not. But one, like when we talk about the earliest supernova observations, we talk about Crab Nebula, and the fact that we can still see the nebula and the neutron star till now, it's like really tells us how the whole thing is evolving, whole system is evolving till now.
Ma'am, in the previous question, that is about the crab nebula question, I picked the wrong crab nebula and it's showing incorrect.
Okay, I
Yeah,
can't.
same problem.
All right, yeah, I can't help you with that, but yeah, consider your answer as being correct.
Correct. Yeah.
Yeah, you might want to add a point to
Yeah.
whatever you got.
So yeah, we are also doing this for the first time. We'll take care of these hiccups next time, I guess.
Yeah.
Okay.
Yeah, the next question is neutron degeneracy pressure fails after three solar mass core, and that's it's a true or false question. I think most of you have answered. I'll give you another 10 seconds to do it, so please finish. I think certain people in certain mini project groups should know this very well. Okay, yeah. Aman, you can kind of explain this a bit.
Yeah, so like I said in the talk, when the core is, when the star is of 12 solar mass, it will eject material and the core will be around 2 to 3 solar mass. So that core's gravitational contracted can be handled by the neutron degeneracy pressure. But after that, we have the gravitational contraction is just unabated. It cannot be stopped by any degeneracy pressure, and we have black holes forming. And again, after the 2 3 solar mass, we have a gap between neutron stars and black holes, which we have observationally we have never found stars in that gap. But in a recent observation, I guess it was 1908 14 gravitational wave observation, we found neutron stars, not visibly, not through any observation of radiation, but from observation of gravitational waves, we found neutron stars in those gaps. So yeah, so that gap is getting populated. We also have another gap on between the lower mass black holes and the upper mass black holes, and that in that gap also we recently found in, I guess, 1904 25. These are gravitational wave observations are coded in different format. So in that observation we found black holes in that gap also. So it's a very, this is a very current and very current topic which research is going on, that why is this happening in this gap, and where does this neutron degeneracy pressure breaks, how theoretically we can predict all these things.
I think even explanations for how for the formation of intermediate mass black holes is a bit of
Yeah,
a
yeah.
very active research field. And
Yes, yes, it is. And after this observation, very recent observation, I guess 2 weeks ago, very recent observation, it's like we all have to understand particle physics standard model, and why is it predicting this gap, and why are we seeing uh, black holes in those gap. It's a very burning question right now.
okay, I think this is the last question, guys. So
Hmm.
gear up.
Yeah.
Complete this sequence: solar mass greater than giant, greater than dash, greater than white dwarf.
So it's not greater than. I'm sorry for again putting it in this.
Larger.
No, no, it's going to. It's a solar mass going to giant,
Oh,
going to
sorry,
what,
sorry.
going to white dwarf.
Okay,
It's
okay,
the sequence. Complete the sequence.
okay, okay. Got it.
I gave my answer done.
Yeah, so I kind of paused the timer so if some of you got confused. So yeah, like he said, this is a sequence
Yeah.
in kind of like the evolution of the star, and it's
Yes.
not a size comparison. So please think and answer.
I clicked on answer because timer is running out.
No, but you can. I think you can change your answer, right?
We can.
I don't know
Oh
if the
no, you can't.
question. Oh, okay, you
No, we
can't. I see. Okay. Yeah, I think a few more people have to answer. I'm closing the question. So all right, I'm gonna go ahead and close it. Okay, we come to an end of the quiz.
So, just a quick comment. I think I described the evolution of solar mass stars very in great detail over here in this, that it will go to a giant and it will go to a planetary nebula, which is the answer, and then form the white dwarfs. So yeah, that's your answer. Okay.
Right. So planetary nebula is the answer, right?
Yes. Yes.
Okay. Yeah, we are at the end. I'm going to just end the quiz. I think we can see the results in a second. I don't know. Okay. Okay. There is Pragnya who stands in the first place. So congratulations, Pragnya.
Congratulations. Okay.
Thank you.
Yeah. So this quiz was not meant for any credit or sort. I just wanted to have an interactive learning part, and just to see whether you can retain some information from the talk. And that's it. I come to an end of my talk. Thank you for bearing with me. And if you have questions, I will. Yeah, I think we have time I guess five
No,
ten
no
minutes.
problem. Let's just address them quickly for the next
Sure,
10 minutes.
sure.
But so far, thank you, Aman, for explaining everything so well.
Thank
So,
you.
um, one second. Jivan, can I refer to the document for the questions? Or shall I look at the chat?
They can ask directly if they want. They can
Yeah,
unmute
so
themselves.
actually at this point, those of you who want to ask, you can unmute and ask. But please, if someone else has started to talk, don't interfere. That's all. But you're free now to just unmute and ask a question.
Okay.
Hello.
My
Hello.
name is. Okay.
Yeah, I think
You
Aditya is
are.
talking. Aditya, go first.
Okay. Yeah. My name is Aditya, and I was wondering, won't the red shifting and blue shifting, due to the relative motion of the stars, affect the spectral regions of which we are able to capture? How is this connected and accounted for? Is it to do with the Hubble constant?
Yeah. So the Hubble constant question is like a very advanced question. I have to be honest. I don't know much about that Hubble constant, the redshift and blue shift. Due to the expansion of the galaxies, I think you mean. So yeah, that is something which we do from gravitational wave observations. We try to perfectly pinpoint Hubble's constant by calculating those shifts. But the redshift and blue shift, which I meant, those the relative motion of the stars, that will shift the spectra totally to the left or to the right, and the spectra would be wholly moved. So we'll have a shifted spectra, and we can calculate the shift and calculate the relative motion. But the characteristic, the curve, the intensity dips and all, they won't change their relative position. So we would still have a very good measurement of the composition of the star.
Okay. Thank you.
Yeah.
Please raise your hand here in the participants.
Hello.
Yeah.
Hello.
Hello.
Yeah. From the laws of thermodynamics, we've learned that the temperature is an intensive quantity. It's not dependent upon its mass. But in
Okay.
stars, we see that it's dependent upon the mass. So I was thinking whether this is a violation of the laws of thermodynamics. I was confused.
Okay, so mass temperature relation, I don't know. I have not put any mass temperature relation, but I would say that the temperature is definitely dependent on how much gravitational energy is pumping in the core and how much contraction is happening. It's a direct effect of that. And also I guess you have to consider an isolated system for the laws to apply. But over here the core is not the isolated system. The outer envelope is also giving in the gravitational energy for the core's temperature to increase. So I think an isolated system would be the whole star, and that whole star temperature varying, whether that violates the first law of thermodynamics, that's a good question. Let me ponder about it a little and get back to you.
Yeah,
All
Aman is
right.
on the Discord server,
Thank you.
guys. So maybe
Yes.
once in a few days he can pop in and kind of answer
Yeah,
questions.
sure. You can just write it to me in that, and I'll think about it a little or
Yeah.
read about it a little, and then maybe I can answer it better.
Yeah, I think Dwij wants to answer. Sorry, ask a question.
Yeah.
Hello, am I audible?
Hello.
Uh, yeah, so in GW astronomy, in gravitational waves astronomy, there is a model known as CE model, which stands for common envelope model, in which two massive stars I mean, one explodes, one evolves into a and becomes a He star, helium star, and then explodes into a supernova, and other also does the same thing, but before in the intermediate part they become um, they form a common envelope.
Okay.
So I was just reading about it and I couldn't understand it, so can you please elaborate about this?
Okay, my knowledge of common, it's called CCE, I guess, CCE evolution, common envelope evolution is very limited. I just know that it's mostly in binary or more than two star system. And when they have the atmosphere is like totally diffuse and there's a common envelope forming. So that is a very again, it's not much known about the CCE evolution. We have population models and different models giving rise to that CCE evolution. But that is a very good contender for the mass gap and all those things I was discussing. So yeah, still research is going on. To be honest, my knowledge is limited in that, so I cannot explain it to you further. But yeah, it's a very active research field. So I'll suggest more reading, I guess. Or yeah, if I can find relevant sources, I'll definitely forward it in the Discord.
Yeah, any last maybe 2 questions? Anybody else?
Ashutosh.
Yeah, can I ask
Yeah.
one?
Sure.
Yeah. See, you just told that the supernova is from the envelope. And how do
Yes.
the heavy elements synthesized in the core get transferred to the envelope so that it is again emitted across the universe?
No, no. So the core is contracting. So the core is breaking down its heavier elements again to helium and protons and neutrons. But the envelope is also made of hydrogen helium. And when the contraction of the core is happening, it is transferring energy to the envelope. So that envelope is in turn starting its own fusion process of hydrogen helium fusing to form carbon, nitrogen, and other heavier elements. So this fusion happens. There are different processes which I didn't want to get into, the S process, R process. They come from particle physics. They enrich the envelope in the heavier element side, and then when the supernova happens, the envelope is only ejected. No material from the core goes to the envelope. The envelope is ejected, and that envelope already contains the heavier elements and the light envelope elements, which are thrown away into the interstellar medium.
Okay, thank you.
Okay.
Okay, I have a question like, uh, can we create a star here on Earth
The,
using
yeah, so
the
that's
same
a
mechanism?
that's a very good question. No, so there's a very good trend again in HR diagram where we have these lines, different lines. So anywhere you start in the HR diagram, you traverse a path. So when you start with something which is even smaller than the Earth, you cannot surpass the electron degeneracy pressure, or the pressure which is even initiated before the electron degeneracy pressure. That is what you'll form a planetary or a planet. Anything of the size of Earth or Jupiter itself. Jupiter is a gas giant. It's just accumulation of a gas. So when you cannot start the processes of the nuclear fusion, the hydrogen burning in the core, that is when a planet is formed. So anything on Earth you will form is, I guess, a very small form of a planet, not a star.
So
Okay.
the
Um,
fact that you can initiate fusion doesn't mean you have created a star, right? So even if we do succeed at nuclear fusion, it will
Yeah.
not, right?
No, yeah, so no. Again, there's a barrier in the diagram, the HR diagram barrier, which you have to cross to go to the star forming region. And I'll definitely share this on Discord. There's one the next speaker, I think Alan is from ICTS. So there's a very good series of talks in ICTS, which are the compact stars talk by Dr. Devanjan, I guess. So in that, he very nicely explains how do you cross that barrier, and if you're not crossing that barrier, you just form a planet. You won't form a star.
Okay.
Also,
what is
continuing the
black
same.
body?
What is
Yeah.
black
Okay,
body?
answer that one.
Yeah. Okay, so black body is basically we have we just take a body which radiates all forms of wavelength. It radiates in the whole spectrum, but it will radiate at a peak wavelength, and that peak wavelength is decided by the temperature of that black body. That is what we consider as black body radiation. Uh, in I think it comes we studied this in statistical mechanics, or even in 11 12 in the stat mech portion we studied this.
Okay, so continuing with my previous question, like
Okay.
formation of star, and you said we can form a planet.
Okay.
So in the space, when a star failed and the core remained, and the dust accumulated on its surface, and a giant dirt ball happened, which turned into a planet.
Yeah.
Where did that dust come from? Like the soil and the magma and stuff.
So that is what you're asking is how
Planetary
are
formation.
how is yeah you're basically talking about planetary formation. I'll also tell you one thing that even if you don't start fusion, you can form I don't know which fusion, but there's some process by which you can form a brown dwarf, which is between a planet and a protostar. So that is also there. This is I wanted to add. But basically, how are planets like Earth formed is like you have a huge cloud, and that huge cloud there are many theories of formation of solar system, so I'm just discussing one theory. So there's a huge cloud that rotates, and that rotation, it forms a protostar in the middle, but the leftover gas, all the gas doesn't fall into the protostar. So there's a leftover gas which is again has a angular momentum and is also spinning. So that leftover gas, it accumulates into small planets, and that is how like the solar system is formed. So that is what I guess even if you start with a globular cluster, so the nebulae are called a nursery of stars. The nebulae is a huge gas cloud, and they will have collapse at different positions, and they will form stars. So even at those localized, those different positions where the collapse is happening, all the star doesn't fall, all the gas doesn't fall into the star. Some gas is thrown off, or some gas remains in the vicinity. So we have planets revolving around those stars, and that is what we do when we do the extraterrestrial search, the SETI search, when we search for planets orbiting around these stars, and we try to look in the dip of their luminosity. So the planets are formed by the leftover gas, I will say.
Okay.
Yeah, I think we'll stop here because Aman's been talking for really long. So let's give
Yeah.
him a break, guys.
No
So
problem.
if
You can
you,
all just one thing, sir. Yeah, you can all forward the other questions also to me in Discord, and I'll try to answer them as much as possible. And
yeah.
thank you for allowing me to speak for so long and for this invitation too.
Yeah, I think it was really, really informative. So
Thank you.
I'm sure all of you guys wanted to, strengthen your foundations in astrophysics. So such questions are really important and we encourage it. So I think Equinox Lounge, you can drop it over there. Maybe you can even tag Aman because he's just joined our Discord. So you can just tag him and leave the question. All right. So once again, Aman, thank you so much. I mean, just the effort you put in and all the knowledge you've shared today, it's incredible. So
Thank
thank you
you.
so much for being a part of this.
Thank you so
So
much.
yeah, we'll see you all in the next lecture. And Aman's going to be coming back in the upcoming weeks as well. So there will be more interesting topics to explore with him. So
Yes.
yeah, thank you to the participants for being here and for listening patiently. So all right,
See you guys.
see you guys all. Bye.